Okay, suppose I receive M interest payments at a rate of R over M per annum. And the way we represent this is as 1 plus R over M all to the power of M. Now, the form that this is in is a discretely compounded return. Now, in this video, what I want to do is convert this discretely compounded return to a continuously compounded return. And the first thing we do is take the logarithm of this. So we have log of A equals M log of 1 plus R over M. Remember, if we take the logarithm of this, the M just comes down. Now what we do is just take the exponent of this. So we have e to the log of A equals e to the M log of 1 plus R over M. So let this be a function in its own right, and we can call this f of R. So if we rewrite this, remember e to the log of A is just A, so this becomes e to the power M times f of R, and we can use the Taylor series expansion to expand the f of R. So f of R equals log of 1 plus R over M. So remember, just a reminder of the Taylor series expansion. So suppose we have a function f of x and we want to approximate it at x naught. So technically we're using the Maclaurin series. So f of x is approximately f of x naught plus the first derivative of the function at x naught multiplied by x subtract x naught plus the second derivative of the function at x naught multiplied by x naught x take away x naught to the power 2 all over 2 factorial plus the third derivative at x naught times x take away x naught to the power 3 factorial, and so on. Okay, so similarly for our function f of r, we would have f of r is approximately equal to f of r naught plus the first derivative at r naught times r take away r naught plus the second derivative at r naught times r take away r naught to the power 2 all over 2 factorial plus, and so on. So let's actually do this. Okay, first let's evaluate the function f of r at r equals 0. So this just equals to log of 1, which is 0. The first derivative of the function is 1 over 1 plus r over m times it by the coefficient of r, which is 1 over m. So we're just using the chain rule here, and we can represent this as 1 plus r over m to the exponent of negative 1 multiplied by 1 over m. So let's evaluate this at r equals 0. If we substitute r equal to 0 here, we'll just simply have 1 over m. So the second derivative is, so bring down the exponent, so we have negative 1 over m, 1 plus r over m. Subtract 1 from the exponent, so we have negative 2 multiplied by the coefficient of r, which is 1 over m, and this equals to negative 1 over m squared, 1 plus r over m to the exponent of negative 2. So if we evaluate this at r equals 0, we would have negative 1 over m squared. Now all we have to do is substitute this into the expansion. Okay, so we would have f of r equals, approximately equals to f of r naught, which is 0, plus the first derivative at r naught, which is 1 over m, multiplied by r, take away r naught, which is 0, plus the second derivative at r naught, which is negative 1 over m squared, times r, take away r naught, which is 0, to the power 2, and 2 factorial, and so on. So this equals to r over m negative r squared 2m squared, and so on. So what we usually do is ignore all the higher terms. So f of r is approximately r over m, and now what we do is substitute this back into this. So we would have a equals e to the m multiplied by r over m. The m's cancel, so we would end up with e to the power r. So, and after a time t, we would have a equals to e to the power of r t.